Okay, work part four, the final part on this. Let's deal with the kinds of problems where you're, say, lifting a rope that's tied to a bucket or a chain that's tied to an anchor or something like that. Now, if you have an anchor one and the anchor's hanging not in the water, that's pretty simple. But as soon as you put it into the water, there's some buoyancy that the anchor gains, and so those problems get pretty complicated. So I tend to avoid those and think more of, let's say there's a person. You're going to love my pictures here, trying to lift a bucket of, let's say, tar from the ground up to the top of a 20-foot building. And the bucket weighs 100 pounds. And he's not only lifting the bucket, but he's lifting this rope, which let's say weighs let's say a tenth of a pound per foot. Okay? So they're going to lift it. He's going to lift the rope and the bucket to the top of the building. Now, this is simple enough that you could just figure out the work to lift the 100 pounds times 20 feet takes 2,000 foot-pounds. And then the rope, which is 20 feet times 0.1, which is 2 pounds of rope, lifting, you can use the average, lifting at 10 feet, and that would give you the answer. You could do it that way. But if you were only going to do it a halfway, then it gets a little trickier and so on. So let's just talk about the calculus on this. Now, there's two ways to look at this, and sometimes the students need to see both ways so that they can kind of get an idea of how this works. So I'm going to set it up the two ways. My students like to make up and down the y direction. So I'm going to go up and down as the y direction, and I can put the coordinate system at the top or at the bottom. I don't care. I'll put it at the bottom. So y. Going up and down. So force times distance is the work. And the work I've got to do is the force has got to be a weight. So it's going to be 100 pounds plus the weight of the rope, which I'm going to say is 20 feet times 0.1 pounds per foot. 20 feet times 0.1 pounds per foot. But the rope length is going to change. So it starts out 20 feet, but if I move it up a little bit, then it becomes whatever I've moved it up, y. So it's minus y. Now the rope is only that long times this. So I have to take the actual length of what rope is left hanging over times the weight per foot, so that's a linear density, times the linear length of the rope, 20 feet minus y, the amount I've lifted it up, and that's the two weights that I'm lifting, and I'm going to lift it up a small amount, dy. And after I lift it up dy, the weight changes, and so then I have a new weight that I'm going to lift a small change, and then a new weight that I'm going to lift a small amount, and a new weight that I'm going to do a small amount. That's one way to look at this, and then I would be integrating it. If I lift it all the way up, y would go from 0 to 20. And 20 minus 20, there would be no weight of rope left, and I've just got the 100 pounds at the top. That's one way to look at this problem. The other way to look at this problem is to say, I've got 100 pounds that I have to lift the 20 feet, plus I got to lift this rope up, and I'm going to think of a small chunk of the rope. That small chunk of a rope has this length. That length times its linear density, 0.1 pounds per foot, times the number of feet, which is a small chunk of it, that I'm going to lift from that position to the top. And that position of that chunk is to the top is 20 minus however high that is. And I'm going to integrate that from 0 to 20. Now, you'll notice that all of the math is exactly the same here. I got the 20 minus y, the 20 minus y. I got this. Here I'm talking about the length of the rope being dy. Here I'm talking about moving it dy, and the length of the rope is 20 minus y. Here, the distance I'm moving it is 20 minus y. So there's two ways to look at how that problem works. And sometimes you might want to show it both ways to your students and let them choose which way seems to make the most sense to them. But that's the idea of how to think about lifting something like a rope tied to a bucket over a building, or an anchor, or some kind of a winch is trying to winch up something. That's the way to think about it.